Hello and welcome back. In this slice of physics, we're going to look at vectors in a different way. We're going to take a geometric look at vectors. We're going to start with discussing components of vectors along the coordinate axes, and then we will discuss the magnitude of vectors and direction represented by an angle. And in doing these things, we will review our trigonometry, which is a key part of what we will be using as we proceed to work with vectors. As we have discussed before, vectors are represented by arrows. In our discussion so far, we have dealt with vectors that lie along the coordinate axes. So for example, if I have my x-axis here and y-axis here, and positives increase to the right, negatives increase to the left, and I've got positives increasing to the top for the y and negatives at the bottom. And so for example, this is a vector. Its magnitude is represented by its length, and along the x-axis that could be whatever it is. Let's say if I have, for example, 2 here and 5 here and x was in meters, I know that the magnitude of this is 3 meters. And we would write the vector as plus 3 meters because it points in the positive direction. So that captures both the magnitude and the direction of the vector. I might have another vector pointing like this, which might be a minus 3 in the y direction. But what if the vector is not neatly lined up along one of these axes? What if it looks like this or that or that? For these vectors, the length of the arrow is still their magnitude, so that part still holds. But how do we specify their direction? We can't say positive or negative. So for example, this vector is moving in the positive direction along the y-axis, but moving in the negative direction along the x-axis. So these are the vectors we're going to discuss now as to how we specify their magnitude and direction. One way to do it would be to specify the components of the vectors along the coordinate axes. So I could say that I start here at the origin, and then I go 8 meters along the x-axis in the positive direction, and also go 6 meters along the y-axis in the positive direction. So I would end up here. So the vector would look like this. And so this vector I specified as plus 8 along the x-axis and plus 6 along the y-axis. Typically, we write the x value first and y value next. So that fully defines this vector, but what is its magnitude and what is its direction? Well, the magnitude, as we discussed, is the length of the arrow. So there it is. But can we determine a numeric value for it? This is where trigonometry comes in. If you know your right triangles, we'll do a quick review of it here. So I'm going to complete this triangle over here. And so now I have an angle here that's 90 degrees. That's what makes this a right triangle. Coordinate axes, by the way, are always perpendicular to each other. And I have two sides of this triangle. And if I have two sides of a right angle triangle, I can get the third using the Pythagorean theorem. The base of this triangle here is 8 meters long, and the height of the triangle is 6 meters long. You know from Pythagorean theorem that if I have a right triangle with base A and height B, and the hypotenuse that's opposite the right angle, and let's say that's C, you know that square of the hypotenuse equals the sum of the square of the other two sides. And so the hypotenuse itself can be written as the square root of the sum of the square of the other two sides. And in this case, we know the two legs, we want the hypotenuse, so that would be square root of 8 squared plus 6 squared, which is 8 squared is 64, 6 squared is 36. Add those two, you get 100. Square root of 100 is 10. And since we're working with units of meters for both of these, the hypotenuse would be 10 meters long, and that's the magnitude of this vector. But what's its direction? Well, we specify the direction in this case as an angle, and here's the angle that we got. Typically, angles are written as Greek letter theta. And this is where I got to quickly review your SOHCAHTOA with you. So if I have a triangle, again a right triangle, And if I have an angle theta over here, the hypotenuse, let's label that H. That's the side that's opposite the right angle. And then whatever our angle is, the side that's opposite our angle is called the opposite side, and the side that's along it is called the adjacent side. The hypotenuse also is along the angle, but that's got the special name of hypotenuse. So the adjacent side is the other side that's adjacent to the angle and not the hypotenuse. And you remember your SOHCAHTOAs from your pre-calc course, and all that means is that this stands for sine is opposite over hypotenuse. So what it's telling you is the sine of that angle theta equals the ratio of the opposite over hypotenuse. The cosine of that angle theta equals the adjacent over hypotenuse. That's where the Ca comes from, CAH. And then for the TOA, we got tangent of the angle equals opposite over adjacent. So these three trigonometric functions are just ratios of sides of a right triangle, and you can remember them using this SOHCAHTOA mnemonic. Okay, so in this case, if I want this angle theta, I've got a choice. I can use any of these functions, but let me just use the opposite and the adjacent. Since those were given to me and I didn't even have to calculate them, I'm just going to use that. So the function that connects opposite and adjacent, if I look at this, is the tangent function, the TOA part of this. So I'm going to write that over here as tangent of theta equals the opposite for this theta angle, which is 6 meters, divided by the adjacent, which is 8 meters. And so theta itself would be tangent inverse, the inverse of the tangent function of 6 over 8. The meters will cancel. And the rest of this can be done on your calculator. You may have to use a second function or something to do tangent inverse of a number in your calculator. And if you do that, you would get 36.87, or rounded to two significant digits, let's just go with 37 degrees. So when somebody gives you the components of the vectors, you can figure out the actual magnitude of the vector and the direction of the vector specified as an angle. In this case, we would say it's 37 degrees above the positive x-axis, or draw a picture and show which angle we mean for the measure we give. And by the way, if you are following along and didn't get 37 degrees when you tried this calculation, check two things. First, make sure that you're taking tangent inverse of 6 over 8 and not just tangent of 6 over 8. Secondly, make sure that your calculator is set to working with angles in degrees and not radians. Otherwise, it'll give the measure of this angle in unit of radians, which we will rarely use in this course. So we just learned how to go from components of a vector to determining its magnitude and direction. But in this case, I've been given a vector as its magnitude of 6 meters per second, it's a velocity vector, and a direction of 30 degrees to the right of the negative y-axis. And I want to determine the components of this vector. So first, the components of a vector along any coordinate axes are the projection of that vector along the coordinate axes. And to do the projection, I need to draw perpendicular lines from the tail of the vector and the tip of the vector to the coordinate axes. And so here's how they look for the y-axis and for the x-axis. So the projection of this vector along the y-axis will look like this, with the arrow pointing down because my original vector points downward. And along the x-axis, it would look like this, with the arrow pointing right because my original vector points right as it goes down. So I can label these two as Vx for the x component of this velocity and Vy for the y component of this velocity. Now, in order to solve for the length of these, it's best to complete the triangle here that's connected to our vector. So I'm going to complete this. And I know that if that's Vy, so is this. This vertical thing here is Vy. And the length of Vx is simply the length of this base over here. And just to rewrite it here, this hypotenuse is given to us as 6 meters per second. So if I want to determine these components, let's do Vx first. For this angle theta, this Vx is the opposite side, and Vy here is the adjacent side next to the angle. And this 6 is the hypotenuse. So to calculate Vx, I need the opposite, and I know the hypotenuse. So the function that ties those two is this sine function, the so part of the SOHCAHTOA. And I can write that as sine of 30 degrees equals opposite over hypotenuse. And the opposite is nothing but Vx. The hypotenuse is 6 meters per second. So now if I multiply both sides by 6, I get Vx equals 6 times sine of 30 degrees, which in your calculator will give you 3, and the unit is meters per second. So that's the magnitude, and since we know that the direction points to the right, we can complete this as a vector by showing the direction as a positive along the x-axis. And for the y component, I need the adjacent, I know the hypotenuse, so the function that ties that is cosine, ka part of the SOHCAHTOA. So this tells me that cosine of 30 degrees equals adjacent over hypotenuse, which gives me Vy over 6. And when I multiply both sides by 6, I get Vy equals 6 times cosine of 30 degrees, which in your calculator will be 5.2 meters per second. And now I know that the direction points downward, which is negative along the y-axis. So in order to complete the vector answer here, Vy vector will be a negative 5.2 meters per second. So those are my answers for the components of these vectors. So in this slice of physics, we took a geometric look at vectors. We learned how to go from components of vectors to magnitude and direction, and to go from vector magnitude and direction to components. And in doing so, we reviewed our SOHCAHTOAs and our trigonometry. Thanks for watching.